I am sure that at some point you've been in water and you've recognized that you weigh less, or that if you're picking something up, that it weighs less. This is because of an idea of buoyancy. So this is a video about buoyancy. And we may as well name the principle right now. This is Archimedes' principle. Here's how it works. When you have an object that's underwater, maybe like this. Let's put a box under the water. Boxes are pretty easy. Box has a depth, well, a height, a width, and a length maybe. And we're going to put this thing underwater. If the top of the box is a distance of d below the surface, that means that the top of the box is getting a depth pressure of rho g d, where rho is the density of the water. I guess it doesn't have to be water. The bottom part is farther underwater. We had d, we are adding h, so on the bottom we get a pressure like this. And that is going to be rho g d plus h. This means that we have a difference. We have a downward pressure of rho g d. We have an upward pressure of rho g d plus h. If we want the forces, that means we will have a downward force of rho g d times the area, right? Because it's a pressure times an area gives us a force. The area of this thing is W times L. So I'm going to write that area is W times L. We get an upward force of rho g d plus h times the area, or rho g d a plus rho g h a. If we look at the difference between these, and yes, we do still have the downward force from gravity from the weight of the block, we'll talk about that in a moment. If we look at the difference between these, our net force from the fluid alone, so I'm ignoring the weight of the box for a moment, our net force from the fluid alone is upward, right? We have this force up, we have that force down, so we're going to have a rho g dA plus rho g ha. That's my upward force, minus a rho g dA is my downward force, because I want to call up my positive direction. I have a positive rho GHA, or rho GDA, and a negative rho GDA. So I get a net force from the fluid of rho GHA. Now I want to look at just what that is. H times A is the height times the area. This thing is the volume of the box. This works, but this actually only works because the whole box is underwater. So let me do just a little bit more with that. if I am underwater partially, so now I am this far underwater. Call that part, I don't know, S for submerged. This whole thing is H. The pressure on the top, I'm not underwater at all, so the pressure from the fluid on the top is 0. I'm saying the air pressure is going to drop off anyway because it's in both. So the pressure from the fluid on top, pressure downward, is 0. The pressure upward is going to be rho g times S. So the force, the net force from the fluid, is going to be rho g S A, and SA, that's the volume of the submerged part of the box. Which was true up here. This is the volume of the submerged part. It's just up here. The entire box was submerged, so it worked. So the volume of the submerged part of the box, the other way to think about that is to say that's how much water had to get out of the way to make room for the box. And that's what Archimedes' principle says. Archimedes' principle says the buoyant force exerted by a fluid is equal to the density of the fluid times G times the volume displaced. Let's think about what this means. If I go swimming in, and the buoyant force is an upward force. If I go swimming in regular water has a density of 1,000 kilograms per cubic meter. If I go swimming in very salty water, like think even the Dead Sea type of thing, if I go swimming in very salty water, the density is higher. If the density of my fluid is higher, gravity's not changing, my volume's not changing. That means that the buoyant force I experience is higher. I get a bigger upward force from the fluid, and that makes it easier to float. Back here, I very deliberately ignored the weight. I'm going to bring it back in now. Let's look at this thing, and this box has a mass of capital M. Now what I've got acting on this box, I have an upward force from the fluid. That is my buoyant force. And it's equal to rho g submerged times area. Submerged height times area. I've got a downward force, and that's equal to m times g. So I could actually find how much of this box will be submerged. If you've noticed, if you drop a wooden box into the water, it floats. If you drop a styrofoam box into the water, it also floats, but they don't float in the same way. We know that something with a density smaller than water is going to float, though we never really talk about why. We know that things don't necessarily float the same way, so let's figure out the why part of that now. Our net force is going to be rho g, and I'm going to say the submerged part of the box, that was meant to be read, the submerged part of the box times the area. This is my buoyant force. My downward force is equal to mg. And that's going to be equal to mass times acceleration, which if I am in equilibrium is going to be 0. So then I have rho GSA equals mg. And if I am solving for how far in this thing sinks, I get this. My gravity cancels, and now I've got the mass of the box divided by the density of the fluid times area. I'm going to do a little bit more with this. I'm going to label this one density of the fluid. Mass of the box. If the box is made of wood, it's got a certain density. If it's made of something else, styrofoam, it's got a different density. The mass of the box I can write as the density of the box times the volume of the box. Now this is not the submerged part of the box, this is the whole box, right? So I'm going to write that S as being density of the box times volume of the box divided by density of the fluid times area. I'm going to do just a little bit more. The volume of the box is the total area times the total height. Area times height, and now that can cancel too. So what I have is an equation that looks like this. S equals density of the box over density of the fluid times H. Or maybe the easiest way to say that would be the submerged part of the box out of the whole thing is equal to the density of the box divided by the density of the fluid. This might not look like a super handy formula, but it really is quite nice. This is only if something's floating. I'll show you why too. This only works if something's floating, because S over H, that's like the percentage of the box that's submerged, right? If I've got this box like this, if I've got a total height of box of 1 meter, let's make it easy numbers, and I can say that this is 60 centimeters, that's submerged. That means this box is 60% submerged. Well, that is 60% submerged. That tells me that the density of the box over the density of the fluid is also 0.6. So the density of the box is 60% of the density of the fluid. If this is water that I'm floating in, and water has a density of 1,000 kilograms per cubic meter, that tells me this box must have a density of 600 kilograms per cubic meter. If I drop a piece of wood, a block of wood, into this same water, a block of wood, and I know that the density of the wood is 700 kilograms per cubic meter, I would say, you know what? I'm going to divide that by the density of the water. And that is 70%. this box is going to float with 70% of itself submerged. Or sometimes the other way that you get that question asked is, what part of the box is sticking out of the water? Well, this is 30% out, 70% submerged. It's a really handy shortcut to have. If I am not floating, if I'm completely underwater, well, I can't do an S that's bigger than H, right? This thing will sink if the density of the box is bigger than the density of the fluid. If I drop something with a density of 1,500 kilograms per cubic meter into the water, that box is going to sink. That means that on the right side, the top of the fraction will be bigger than the bottom of the fraction. On the left side, this fraction is what percentage of the box is sitting under the water. Well, I can't have 150% of the box sitting underwater. That doesn't work. So this formula works for a floating object.